these bounds. C delta t plus n minus 2 into square of logarithm of n. So this is the pollutant term, square of logarithm of n. This pollutant term appears due to the construction of piecewise uniform mass. And again, these estimates, and to get the error estimate for the purpose finite difference scheme, we combine the error estimate for the smooth component and singular component and arrive at these following parameter uniform error estimates. And these parameter uniform error estimates shows that our proposed scheme is first order accurate in time and up to second order accurate in space up to this logarithm factor. ठीक है, when epsilon is less than equal to n to the power minus 1. Now our scheme is almost second order accurate in space but first order accurate in time. So to enhance the accuracy in time, we employ the Richardson extrapolation technique in time direction only. And Richardson, so we take the mass points as it is in the space direction, but in the time t, we consider the mass omega bar t kn, where k equal to 1 2 with step size delta t by k. So we let d bar nm equal to d bar nm intersection d bar n2m, and it's clear that d bar nm is equal to d bar nm. And let ukxitj, where u1 is the solution on the mass d bar nm and u2 is the kn, where k equal to 1 2 with steps the problem size delta t by k with respect to the. So we let d bar nm equal scheme. We apply the same finite difference scheme on the mass d bar nm and d bar n2m, and we are letting the discrete solution is u1 and u2 respectively correspond to the discrete scheme 6. Now we take the linear combination of these two solutions in this way, 2u2 xitj minus u1 xitj. So in this way, lower order truncation error estimate will get vanished in time direction, and we get a second order accuracy in time direction. So that's why after applying, and this solution u bar xitj we consider as a Richardson extrapolated finite difference, Richardson extrapolated solution, which is the linear combination of u2 and u1, and that linear combination is defined in this equation number 40. So thus, after applying the Richardson extrapolation convergence enhanced technique, our proposed scheme is second order accurate in both space and time direction up to this logarithm factor. Now, to validate our theoretical estimates which we derived, we consider this problem as a test problem and apply the proposed finite difference scheme. So since above problem do not have the exact solution, so to analyze the order of convergence and maximum pointwise error numerically, we consider the following double mass principle. So we consider u bar 2 and delta t by 2, that is the exact solution, and derive these pointwise error estimate in this way by using double mass principle. So when u hat n delta t equal to u n delta t, when we apply fully discrete scheme without Richardson extrapolation, and u hat n delta t equal to u bar n delta t when we apply the Richardson extrapolation scheme. Then maximum nodal error is calculated by using this formula. Parameter uniform maximum pointwise error is calculated by this formula. Further, numerical order of convergence and epsilon uniform order of convergence are calculated by these formula respectively for fixed value of rho. So in table 1, we begin with 32 mass points in the space direction and with delta t equal to 0.25 by 2 in the time direction, and at the with each step we double the mass points in space direction and also reduce the mass width in time direction by 2 with each successive iteration. And note that resultant scheme is first or almost first order accurate. You can see you are getting first row is giving the epsilon maximum pointwise error, and second row is correspond to the order of convergence. So one can see, if you notice this second row, over a scheme without Richardson extrapolation is first order convergent in time and second order accurate in space. But we are not reaching up to 2, we are reaching up to 1.10. Basically, in these numerical results, we are not depicting the second order accuracy in space. That is due to the error in the time direction dominate the error in the space direction, and this order of convergence is correspond to the totally finite difference scheme. So to show the theoretical error, theoretical order of convergence in space, we begin with n equal to n equal to 32, and at the next iteration we double the mass points in the space direction, but in time direction we divide the mass width by 4 each iteration. So in this way you can see order of convergence is looking at up to 2, and this is order of convergence is correspond to the order of convergence in space direction only. So in this way we validate the over theoretical error estimate that our totally discrete scheme is second order accurate in space. And again we apply the discrete scheme 6 without Richardson extrapolation. Now to show that Richardson extrapolated scheme is second order accurate in both space and time, again we begin with n equal to 32 in space direction, and for next step we double the mass points in with each step, and again delta t equal to 0.25 by 2, and with each step we divide the delta t by 2 only. That is, we are not dividing here by 4. And note that correspond to each epsilon over scheme as number of mass points increasing, over scheme is up to second order accurate, and it validates that over Richardson extrapolation scheme is second order accurate in both space and time. So this is a numerical solution plot for example 1 with m equal to n equal to 64 with epsilon equal to 1. So note that solution is smooth, correspond to epsilon equal to 1. If epsilon getting smaller, epsilon equal to 10 to the power minus 3, one can see solution changes rapidly at the point 0t. So our interior layer form around the point 0t, which is visible over here. So here a robust higher order finite difference scheme is used to approximate the time dependent singularly perturbed interior turning point problem. Solution to this problem class having an interior layer in the neighborhood of turning point under this assumption. If lambda is less than 0, then 2 outflow boundary layer will appear. So a layer adopted piecewise uniform mesh is constructed in space direction, which is finer in the layer region and coheres outside the layer region. The hybrid finite robust numerical scheme constructed, which comprises the implicit Euler scheme in time direction and a hybrid scheme which combine the midpoint of wind and center difference operator in space direction. In table 1, we show the accuracy, show that scheme is first order accurate because error in the temporal direction is dominate the error in the spatial direction. In table 2, again we apply the our constructed finite difference scheme 6 without Richardson extrapolation, But in table 2, we find out the temporal mass by dividing delta t by 4 and multiply n by 2, which give almost second order accurate in both the direction. And it reflects the order of convergence in the space direction. So, an convergence acceleration technique called dispersion extrapolation scheme is used in the temporal direction to establish a higher order accuracy in the time direction. The numerical results in table 3 is in good agreement with our theoretical finding, that is shown that after applying dispersion extrapolation technique, resultant scheme is second order accurate in both space and time. So these are the some references. This work recently published in the journal Mathematics and Computers in Simulation. If someone interested in this work, so they can ask me, or I will send you that paper, and otherwise you may download from the journal website. I think I am on time. Yeah. Okay, thank you. Is there any question? Okay. Okay, thank you. Thanks a lot. Hmm.
Yes, I'm here. Okay. A very good morning to everyone. I'm Dr. Rimpi Pal Kundu, Assistant Professor in Gargi College, University of Delhi. And it is a matter of great pleasure for me to be able to showcase my research in this platform. So thank you very much for this opportunity. So I'm starting my presentation. I hope my screen is visible to everyone. And am I audible also? Okay, thank you so much. Okay, so the title of my presentation is Adaptive Function Synchronization Based Secure Communications of Modified Time Delayed Cheney Systems. Firstly, to begin with, I will give you an outline of the work that has been showcased here. Like in this paper, we have obtained hybrid projective function synchronization of two identical time delayed Cheney systems, each starting with different initial conditions. And the process which we've used to synchronize the two systems is adaptive control method. Further, the systems which we have synchronized here are time delayed systems, the time delays being discretized. And after the obtainment of synchronization in both the systems, we have used them as proposed models to obtain a case of secure communication system by choosing one of the systems as the sender system and the other system as the receiver system. Why we have chosen a time delayed systems, the reason being that when we are showcasing a communication procedure, the presence of time delays strengthens the communication procedure, and hence we have actually chosen time delayed systems for the process. And further, we have also used modified chaotic masking scheme to establish this communication effectively. To establish the communication scheme, we have chosen continuous functions of time t as the messages, and we have shown later on that these messages have been communicated in between the systems with very high level of accuracy. And further, our analytical findings are also supported by the numerical simulations effectively. Now, to begin with, let us let us introduce ourselves to the Cheney system. Now, what is a Cheney system? Is one of the novel chaotic systems devised by Chen and Lee some decades ago. Like we have had more than 33 dimensional independent systems of these kinds, and Chen Lee is one of them. And Chen Lee is capable of producing a very sophisticated chaotic attractor. Because of this reason, we have chosen this Chen Lee system as our proposed model. Now, the system of the equations of motion of the Chen Lee system is governed by a set of 3 first-order differential equations given by dx dt equal to minus yz plus ay, dy dt is equal to yz plus by, dz dt is equal to 1 by 3y plus cz, where a, b, c's are the system parameters and x, y, z are the state variables. All are time dependent. Now, just as I said, we are our basic aim in this work is to obtain, firstly, the phenomena of synchronization, chaos synchronization between the two systems. So we have chosen 2 identical Chen Lee systems, but each starting with different initial conditions. And we call one of the system as the master system. The equations of motion are governed by the x variable system, as it can be seen here. And the slave system which has to be synchronized with the master system has been, the equations of motions are governed by the y set of variables. Apart from the difference in the state variables, there are some other differences as well. For example, in the master system, A, B, C are denoting the parameters which are certain in nature. Certain in nature means these are constants and not time dependent. Whereas in the slave system, the parameters involved are named as A1, B1, C1, and these are time dependent. These are uncertain time varying parameters. So when we have to synchronize those systems, we also have to see that the parameters are also tending to the certain values of the master system. Now, K1, K2, K3 are the feedback terms added to the system because of the presence of the time delays in the system. Now, to begin with, the synchronization procedure, let us have a bit of an idea that what exactly chaos synchronization is. Now, chaos synchronization, as the term, the term is very understandable, literally as, yes, ma'am. Chaos synchronization is understandable literally also. When we have 2 chaotic systems, chaos in itself means a system where we cannot predict the trajectories of the system in future, how they will be moving in future. It is unpredictable. So chaotic systems are in general not predictable. So we have to have some ways of determining their trajectories in future. And chaos synchronization is one of the procedure by which we can control the dynamics of the chaotic systems. Now, what happens in a chaos synchronization procedure is that we have 2 different chaotic systems. These chaotic systems can be either identical with different time, with different initial conditions, or they can also be non-identical. And what we try to do is we try to force the dynamics of one of the chaotic systems to follow the dynamics of the other chaotic systems. And when it does so, we say that synchronization between the 2 systems have been achieved. So the idea of synchronization is to use the output of master system to control the slave system so that the output of the response system follows the output of the master system asymptotically. No, asymptotically means as time tends to infinity, that is forever. That is, we apply the process in such a way that the synchronization is achieved forever, for all time. And now many techniques are available for applying chaos synchronization, namely say the PC method, the OGY method, time delay feedback method, backstepping method, adaptive control method, etc. Now, in this paper, we have showcased the adaptive control methodology for obtaining synchronization. Now, before moving on to the control procedure, let us talk about the different types of synchronization processes that we can achieve. Now, it completely depends upon the type of scaling function that we have chosen, that what kind of synchronization we are going to achieve. Now we name this scaling function as alpha t, for example, here. And since we are calling it as a scaling function, so this is time dependent. So we have called it as alpha t. That is a function of time t. And if the system has, say, n set of state variables, so for these each set of n variables, we will be having n different alphas. So that alpha t is basically a matrix of order n cross 1, where the values are alpha 1t, alpha 2t, and alpha nt's respectively. Now, depending upon these scaling functions, we define the error variables, which are given as ERT is equal to XRT minus alpha RT YRT. So that it can be clearly seen from the definition of the error variables that as the error variables tend to 0, XRT tends to alpha RT times YRT. That is, XRT synchronizes to YRT by a scaling function alpha RT. So this is the concept of synchronization. So it is very clear that by choosing different values for alpha RT, we can have different types of synchronization processes possible. Now, a very few famous ones I've named here. For example, the first one is complete synchronization. In complete synchronization, what we try to do is we try to completely synchronize the X system with the Y system. The Y system with the X system. That is, the Y system completely agrees with the X system. So here the values of all the alphas are chosen as 1. Now in anti-synchronization, what happens is ERT is given by XRT plus YRT. It implies that as the error variables become 0, XRT is equal to minus YRT. That is, XRT synchronizes with YRT, but in opposite directions. They become mirror images of each other. We can also have the case of projective synchronization. In projective synchronization, ERT is given by XRT minus alpha YRT. Now, alpha here means it's a scalar. It is not a function of time. So that it implies that if I choose the value of alpha, I say 2. So it means that XRT is getting synchronized with 2 times YRT. Okay, that is YRT gets scaled down by 2 times when I choose alpha as 2. So that, and if I choose alpha as 5, then YRT system, that is the slave system, gets scaled down 5 times. So this is the this technique is called as projective synchronization technique. Further, we can also have hybrid synchronization. Here, the scaling functions are again scalars, but they are different for different state variables. And lastly, we can also have the case of function synchronization, where each scaling function is a function of time t. So that we have further, like this is the most generalized case of synchronization as can be seen, that we can choose the scaling functions not to be just scalars, but also as any function of, any continuous function of time. Now, in our research work, we have found hybrid function projective synchronization. I've already explained the meanings of the word hybrid, function, and projective. So we have fused all these cases together to obtain hybrid function projective synchronization. And here the error variables are given by XRT minus alpha RT into YRT. And since Cheney system is a system of 3 first order differential equations, so R runs from 1 to 3. Now, as this is the system of error equation, error variables, when we derive this, when we find derivative of this system with respect to time t, the system of all the derivatives of error variables can be looks like this. ER dot is given by XR dot minus alpha dot into YR minus alpha dot, YR dot into alpha R, where R runs from 1 to 3. Now, when we write these equations, this system of equations for R equal to 1, 2, 3, we get a system of equation, that is equation of motion of the error variables. And hence, this system of equations is called as the error dynamical system. And hence, what we seek is to stabilize this error dynamical system. Now, clearly, since the Cheney system comprises of 3 differential equations, So the scaling factor alpha t will be determined by this matrix alpha 1t, alpha 2t, and alpha 3t, where each of the alphas are continuous functions of time t. Now further, now after understanding the process of synchronization, now we come to the process applied to achieve synchronization. As already mentioned, we have different control schemes to obtain the process of chaos synchronization. One of the most important and used control schemes is adaptive control scheme. Adaptive word refers to adapting itself to the changes which come with time varying entities. As we have already seen that the slave system considered in this case contains time dependent uncertain parameters given by A1, B1, C1. Hence, to incorporate those adaptive features, we have to we follow this adaptive control scheme. Now, in a very short way, I would like to just explain the process here. In this process, we firstly propose the adaptive control laws, where the controllers given by the controllers which are added to the slave system, and hence the slave system becomes synchronized, that are controllers. So the controllers here are determined by the adaptive control laws. Further, we also propose parameter update laws, where the parameters which are time dependent are also determined by these parameter update laws, and together together these laws are put into the error dynamical systems. And once we do that, we find that the system gets stabilized and all the error variables asymptotically tend to 0, showing that the system is getting stabilized. Now, for this particular case of the Chinese systems, the adaptive control laws were proposed as this. The parameter adaptation laws were proposed as this. Further, analytically to show, before we move on to the numerical part, we also performed stability analysis, and stability analysis is performed by considering Lyapunov-Kraskovsky functional given by this. We know that any Lyapunov function determines a system's stability, where V is chosen as a function which is non-negative in nature. For this, we have chosen V as squares of all the variables involved, and it can be shown by using all the control laws and the parameter update laws that the time derivative of this Lyapunov-Kraskovsky functional is less than 0. So as it is less than 0, by Lyapunov stability theorem, it can be proved that the aerodynamical system is stable and all the error variables tend to 0. That is the origin, is the point of stability, and all the error variables tend to 0. And as the error variable tends to 0, all the x variables get synchronized with the y variables up to a scaling function determined by alpha RT. Now, these are the numerical simulations which have been performed. These are the three-dimensional phase portraits of the master system, the slave system. Now, this is the Cheney system, which is chosen as the master system. It is a chaotic system. And this is the slave system, that is the same Cheney system, but starting with a different set of initial conditions. Since it is a chaotic system, hence it is very, very sensitive to initial conditions. Hence, even with very slight difference in initial conditions, the dynamics of the two systems can look very different. Now, this is a slave system without the controls. We can clearly see that the two systems, they don't look alike. The phase portraits are very different from each other. Now, this is the slave system under complete synchronization, when we add controllers to achieve complete synchronization. In this, the slave system looks like this. We can compare it with the previous one. So we can see that under complete synchronization, the phase portraits look very much alike. Now, coming to the second figure, this is the superimposed image of master system and the slave system under anti-synchronization. Now, as I had already mentioned that anti-synchronization, here the error variables are given by XRT plus YRT, so that as ERTs tend to 0, all the XRTs tend to minus YR0. That is, the slave system and the master system, they get synchronized, but in opposite direction, so that the face portraits are mirror images of each other, and it is very clearly visible from the figures. We can clearly see here that the red one shows the master system, while the blue one shows the slave system, and they are mirror images of each other. Now, coming to the next face portrait, this is the superimposed image of the masters and the slave system under projective synchronization. Now, as I had already mentioned, projective synchronization refers to the case where the scaling function is a scalar, and these scalars here are chosen as 2, 2, 2. That is, each of the state variable gets synchronized with the corresponding state variable of the master system by unit of 2. So see, it can be clearly seen here. It can be clearly seen here that this blue one shows the image of the master system, and the red one shows the face portrait of the slave system. And when we chose alphas as 2, 2, 2, each of the state variables have been scaled down by 2 units. It can be very clearly seen from the superimposed images. Now, this is a case of function synchronization where the alpha t has been chosen as different functions of time t. And for this, like the synchronized images are shown from here. Now, this is the error graphs. See, the time evolution of the error graphs also shows that as time passes, asymptotically, all the variables tend to 0. Now, after successfully achieving synchronization, hybrid function projective synchronization between two Chenley systems starting from different initial conditions, we show its application in the system of secure communications. Now, secure communications, the concept of secure communication means that we have two systems. One of the system is called as the sender system, and the other system is called as the receiver system. And we want to like send a secret message from the sender to the receiver, and we want to retrieve that message successfully from the receiver with very high level of accuracy. And for this process, we have used this chaotic masking scheme, and this process of synchronization has been shown as an application here. So quickly just discussing the steps here. Like firstly, a secret message, which is called as say MT, is to be securely communicated from the sender system to the receiver system, so that when I apply this to the chaos synchronization scheme, my original master scheme, my master system becomes the sender system now, and the slave system, which was originally originally referred to, now becomes the receiver system. So with this modified way of calling the systems, we have this modified chaos masking scheme where the secret message, which is given by MT, it is scaled k times and is added to one or more than one variables at the center, and then it is transmitted to the receiver. Now, when the secret message is added to another variable, we are actually trying to mask this secret message using the state variables, and hence the name as masking scheme. That is, we are trying to cover the secret message into some variable of the state variables of the system. Now, we obtain complete synchronization between the two systems, and then the secret message, which was added to say X2 and X3 at the sender, it is retrieved from Y2 and Y3, which have got synchronized with X2 and X3 respectively, and you obtain the original message by scaling it down k times. Now, this is a schematic diagram of the communication scheme here. We can clearly see that MT is scaled k times and added to X3, and now this is called as ST. It has been added to this X system, which is the master system. This is also called as the sender system. Then this X system gets synchronized, completely synchronized with the Y system, and then this the secret message is again retrieved in the form of M1T, and when we retrieve it, we scale it down k times to receive the original message. Now, for applying this chaos masking scheme, we have to firstly modify the master system and this slave system accordingly, so that this method can be applied. And after doing this, we perform complete synchronization between the two modified master and the slave system using the same controllers as before. You don't have to, find other set of controllers. The same controllers can be used to synchronize this modified system. And then we retrieve the secret message, which was in the form of empty before, as M1T. As an example, we have chosen MT as t to the power 5 plus 1 here, and we have performed numerical simulations for the same. And we can clearly see that the original message MT before looked like this. The time evolution graph of this message looks like this, while that of the retrieved message also looks very similar, and hence we can confirm very high level of accuracy in the same. So now we can clearly say that hence we have successfully not only been able to achieve hybrid function projective synchronization between the two time delayed Cheney systems, but we have also been successful enough to use them as proposed models, to make them proposed models as sender models and receiver models. And then we applied again the concept of complete synchronization to synchronize both the systems and then obtain the secret message between them. And numerical simulations also confirm our findings in the end. So thank you so much, everyone. Thank you so much, ma'am.
Please share the email ID once again, madam. The first slide, it will share your email ID.
Okay. Thank you so much, ma'am.
You listen me? Hello?
Yes, yes.
Hello, you listen me?
Yeah, you are audible.
Hello, Das, you listen me?
Yes, sir. You are audible.
Hello? You listen me? You listen me? Hello, Das, I can begin. Hello? Hello, Das? You listen me?
Yes, sir, you are absolutely audible. Please continue your presentation.
Hello, Das, you listen me? I can begin. I start. I can begin. I can begin, Das? Hello? Okay. So my talk is entitled Global Existence Blow Up Infinite Time Entering Bifurcation of Some Biological Systems. My objective in this conference is to present to the colleagues to pay attention to the global existence of the solution when they study the Hopf bifurcation for the ordinary differentiations and the Turing instability for the partial differential equations. I take as example this system, system of okay. I continue.
Yes.
I continue.
Yes, sir. Continue.
Okay. Thank you.
I said continue.
I take this example of Aziz Alawi, published in 2002. The problem is with this equation, with the top predator. The third equation, the third equation blows up at finite time. To see this, I take the ordinary difference equation associated, and we show that this solution tends to infinity as t tends to finite times. And so we can't study the bifurcation, the Hopf bifurcation, and we can study the Turing instability. When C is greater than W3 over D3, we have automatically blow up at finite time. You see this the third equation by comparison with ordinary difference equation, we have blow up. We show also that when C is less than this, than W3 and W3, we have always blow up. We compare with we take this comparison and we prove that the denominator of this tends to infinity as t tends vers t max. And so we can't study the bifurcation. The bifurcation because t is not infinity. When the initial conditions are also small, we have this proof. And we prove always we have not global existence, and so we can't speak anything about the bifurcation or the Turing instability. We have this theorem, limit RT as t tends to infinity, K plus infinity. I shall give in this some techniques to prove global existence. To prove global existence, we have three techniques. To prove global existence, we have three techniques. the technique of semigroups. I give some example of semigroups. For example, the group of translation, the group of finite group, the group center of generator matrix, defined by this by 20. We have to prove global existence via semigroups. We use this theorem of Hide-Yoshida. We have this condition sufficient and necessary condition to get global existence. Example of diffusion operator. We have many examples. We use the weak maximal principle of the diffusion. We have here to prove global existence. We have three, as I talked, we have three techniques: method comparison with corresponding ordinary differential equations, method of invariant relation, and method based on priori estimates. We use the strong maximal principle. We use also the weak maximal principle. Here we use the comparison of two ordinary differential equations. If the first equation is less than the second equation, also for the boundary conditions and the initial conditions, then the solution U, is less than the solution V. So if you blow up at finite time, then V also, and if V exists globally, then U exists globally in time. This is the equation of Riccati. It blows out as finite time. This is the comparison with the comparison of the partial difference equation with this partial difference equation 46 with the corresponding ordinary differential equation. If YT, if the initial condition of Y is, if we take we can compare always the partial differential equation with the ordinary differential corresponding ordinary differential equation. And we have this. If the ordinary differential equation blows up at finite time, then U blows up. And if Y exists globally, then U exists globally. Where Y the minimum of the initial condition, and this is the maximum of the initial condition, or omega. But to prove global existence by comparison of systems, we need, because we haven't the relation of order, the order relation, so we need this definition that the function, the reaction is called quasi-monotone if we have this condition. The derivative, the partial derivation of Fi is less than 0 for all E different from 0. So we need this condition. If we have this condition isn't satisfied, we can't compare two systems. We can't compare two systems. We take the system. We take this partial differential system and the corresponding differential system. So we have the solution of the partial differential system is less than the corresponding solution of the ordinary differential equation, the ordinary differential system. We have always this alternative for the system 51, partial difference system. We have UT is bounded and the solution exists globally, takes T max, or the solution blows up at finite time. And we can't, in this, when the solution blows up, we can't study the bifurcation or the Turing instability. The method based on invariant region, to simplify, I take this region 60 and the region 61. The intersection is a bounded rectangle, and if the initial conditions, what we mean by invariant region, if the initial conditions is in this region, then the solution continues to live in to continue to exist in this rectangle. If you take any condition in any initial condition in this rectangle, so the solution continues to exist in this rectangle, and it is bounded. If it is bounded, then it is global. I continue, yes, no problem. There is a problem with the internet. The second technique is the invariant region, technique of invariant region. So if you have there is an invariant region, then with a bounded invariant region, then the solution is global, will be global. To see this, to get an invariant region, the condition, this is the condition 64, and the condition 65. The two intersection of these two conditions, we have a bounded rectangle, and the solution is global. To see this, I give an example. I take this example. We do a test. This is a test. We say that this participation system, it have an invariant region, and this condition 68. To see this, we do the test. We have the reaction F1, F2, F3. For U equal 0, we have F1, 0, V greater than 0 in sigma. For V equal V, we have this is greater than 0 in sigma. Then V is greater than B. For W equal C, we have greater than 0, and F3 is greater than 0. Then W is greater than C. Also, for U equal A, we have this is negative. Then U is less than A, it is bounded. For V equal B, we have this. So it is negative, and so V is less than B. So this is the test. For W equal C, we have F3UVC is negative, then W is less than C. Then we have the region, a bounded region. We have a bounded region. This is the region bounded, the region 69. If we take the initial condition in this region, then the solution continue the solution doesn't leave this set, this rectangle, and so continue to be bounded. So we have global existence at time t equal plus l'infini. In this case, we can study the Turing instability or for the partial difference system or the bifurcation for ordinary differential system. The functional method, the continuum method, are based on the functional methods give the estimation a priori of the solution. We say that L is the diagonal function for the system 70, for example, if its derivative is less than 0 and it is positive on the interval of existence 0 to max. The choice of the functional Lyapunov depends on the form of the reaction F and G. For example, if the reaction are polynomials, we say we use this functional. If the reaction are fractional, we use this functional 72.
Sir, please elaborate the last slide. Slide number.
If, for example, the reaction are exponential, we choose the form of the Lyapunov functional 73. To prove that the functional is decreasing, we derive the functional with respect to t, and we use the Green's formula. We find L point, the derivative of L, is the I plus G, two integrals. The integral I contains a quadratic form of gradient U and gradient V, and we prove that it is positive if the discriminant is negative. For the Turing instability, we have studied this system, I think, with Das, with Dr. Das. We construct the matrix, this matrix at the point of the critical point, U1 star, etc. And we apply this theorem. Theorem, sufficient condition that it isn't here. I thank you.
Sir, can you please explore the slide number 85 once again? Hello. Sir, please explain slide number 85.
These are some references. I don't understand, excuse me. Oui, yes? I don't understand, excuse me, yeah? I finished my presentation. I finished my presentation. I thank you. Okay. Okay.
Can you see my slide? Hello.
I try to speak English, but I can't. I don't understand when you speak because I am French. My language is French. Excuse me.
Okay, so then let me start. So I'm thankful to the organizers for giving me an opportunity to share my knowledge for this FDP Faculty Development Program. Myself, Pratibha Das, working on the numerical analysis and well-postness of fractional or integral differential equations, mainly on the PDE side or the system of ODE side. Today itself, I'll be talking about something what is called fractional differential equations. And the title is Introduction to Fractional Differential Equations and its comparison with integral equations and ordinary differential equations. So let me, instead of going to the next slide, let me just tell you that why are you bothering about this fractional side? Because hardly you will see any paper where fractional differential equations are appearing from the modeling. Hardly you will see. What they will do, what you will do, what your students will be also doing is they will be having a model where the model is having ordinary term, ordinary differential term, and that you'll be replacing by a fractional derivative. Just that's all. And then you said that fractional derivatives are having this definition, and whatever result you are getting, that is exactly matching with the ODE. Therefore, fractional derivative is more nearby solution of fractional derivatives and more nearby to the solution of ODE. So fractional derivatives are much more generalized form than ODE. But that is not how it goes. That is not how it goes. So I'll before I go to the next slide again, let me just tell that these fractional derivatives, if you know any application, concrete applications, you let me know. But there are plenty of applications of ODEs, especially because ODEs are having units. Units means we know that if x is the space variable, then d2x dt is the velocity. Velocity is unit also, you know, and d2x dt2 is also acceleration, that unit also, you know. But now my question is, what is the unit for fractional derivatives? That question I am posing as an open question. If you know the answer, then you just post it in the chat box. You just post it in the chat box, I'll be able to see it. And regarding the integral equation term, this integral equation, those, since all of you are more or less faculty, that means you have done your MSc. Since that means you have done your MSc from somewhere, and in MSc you are having a course called ODE, and this ODE definitely will be having something called Picard's theorem. You know what is Picard's theorem? Picard's theorem, what it does, it provides a existence uniqueness for y dash equal to fxy with y at x not equal to y naught. This is for initial values, where f is a nonlinear function. And you also have to assume that f is Lefschetz with respect to the unknown variable, continuous with respect to the known variable. So then what you do is, before going to prove the solution exists and unique, so what you do is we convert that y dash equal to fxy to an integral equation. If you remember the integral equation, what is the integral equation? Y xn plus 1 equal to y xn plus integral x naught to xn f of x comma yn dx. This is the integral equation we got from y dash equal to fxy. That means ODE is closely linked with the integral equations. Because we can do the Wester's-M test and all the other formalities on the integral equation. That is easy, and you can reduce the smoothness also for integral equations. Okay, but when I'm doing the Picard's theorem for ODE, and when I'm doing the proof or Picard's iterative formula, what you know, there, since f is continuous or f is Lefschetz with respect to y, that means the kernel function in the integral equation after converting y dash equal to fxy will be a regular term. Will be regular kernel. But now question is, what is going to happen if that kernel is a singular kernel or weakly singular kernel? So here in fractional derivatives, you will see most of the times the kernel function will coming out to be a singular kernel or logarithmic term for Hadamard derivatives. X minus t to the power minus mu for Caputo fractional derivatives. Derivative will be inside the integral for Caputo derivative and outside the integral for Riemann-Leibniz derivatives. This kind of appearance will be there in when you try to link this integral equation to fractional differential equations. Okay, but I'll still leave an open question to all of you that those who are working on this field, that how to define the unit. Unit means we know the equation of motion. Equation of motion for Newton's third law is d2 by dx equal to mf. That means mass times acceleration. That means we know the equation of motion. What is the unit of the mass? What is the unit of the acceleration? That we know. But for fractional derivatives, simple problem, how do you define the unit? Whatever the solution be, what will be the unit of that fractional derivative? That I'm leaving in question, a question, because more or less you have attended many lectures on fractional derivatives till now. Okay, I hope now my question is clear. Okay, so you try to post those questions or a rough answer or a guess answer in the chat box so that I can see and we can have a discussion on this. Okay, now let me go to the what is called fractional derivative, my way of viewing it, and we will come to what is called. So we'll not go to the research part. We'll mainly walk or move towards the CSIR or GATE or simple whatever we know from basic BSc side. Okay. So now let me come to what is called fractional derivatives first option. You see, in 1695, D. L'Hopital, Yale Hospital, what you call, asked the following question to Leibniz. Leibniz, it is around 300 years before. What is the meaning of what? Someone is someone has muted here. Can you please
خير حكيم.
صباح الخير الحاج، وش الحاله؟
واش اخوي لاباس؟
الله يعافيك، ربي يحفظك هذا الشيء.
Can you please mute Said Kawachi?
المهم انك تستوعب على الناس السنه.
ها ويجيك دوك بعد. هاي داكور صح، بارك الله سمح لنا صحيت صح. صح.
Who is Said Kawachi? Can you please mute yourself? I mean, okay. I don't know whether anyone is listening this or not. Okay. So my screen is visible. Can anyone tell me that my screen is visible or not? Hello, can you see my screen? Yes. Okay. Okay. So just before the 5 minutes of my lecture is over, you just remind me that you have 5 minutes. Okay. So you see that around 300 years before, 325 years before. So this is the question came to Yale Hospital. At that time, the journals are not there. Standard books are also not there. Huh? It is everything is going on how to define the definition of derivative. How to define the definition of derivative. That was the main question of before 300 years. Okay. How to define the definition of derivative. Okay. So you have to understand the question. Okay. So now when during this time, Yale Hospital and Leibniz, of course, they are a little bit mathematician that you know during that contemporary time. So what is the meaning of half-order derivative function? Half-order derivative means, so suppose they are able to find out, they are able to propose a definition of derivative, then that definition, it is having a meaning in terms of limiting procedure. But how to define the half-order derivative? How to define the one-third order derivative? Whether this half-order, to define the half-order derivative, you need function to be one-time differentiable. If a function is one-time differentiable, does it imply that it will be half-time differentiable? Because, why am I asking this question? Because it is a little bit crazy, no? Because if you are demanding half-order differentiability requires one-time differentiability, that means you want more to be of less differentiable. That you don't want. That is one thing. Second thing is, we will also see that if some function is one-time differentiable, it may not imply that it will be half-time differentiable. That is also kind of interesting thing which we will see. Because one-time differentiability does not imply absolute continuity, and absolute continuity is one of the necessary condition for one of the sufficient condition for existence of Caputo functional derivative. Okay, not necessary, so sufficient condition. Okay, so this is the question which was posed 300 years before, and that raises to the definition of what is called Caputo or Riemann-Leibniz, whatever it is. Now let me come to again what is the basic definition of continuity and differentiability. I'm not going to explain the definition of continuity and differentiability. Okay, so this is just for showing you. Okay, but I'll just more I'll ask you the questions rather than giving what is the information. Question is, you know that for a continuity you will have an epsilon into definition, and if this delta given epsilon, there exists delta. That means epsilon is input, delta is output. Okay, and if this delta depends on the epsilon as well as the point, then we call it continuity. Function is continuous at this point. If this delta depends only on the epsilon but not on the point, then we call this function, this definition leads to the uniform continuity. That means if delta is a function of x, then it is continuous. If delta is independent of x not, then it is called uniformly continuous. Okay, this is the definition which you know. That means in some sense, this property, if you look into, continuity is a local property, whereas uniform continuity is supposed to be global property because it's not depending on the point x naught. Okay, supposed to be global property. However, since any continuous function on a compact set will be uniformly continuous, there is a result in since all of you are more or less, there is a result in SK MAPA. You can look into, for example, that any continuous function on a compact set will be uniformly continuous. So that means the moment you are defining the domain to be a compact set, continuity and uniform continuity both are same. There is no difference between these two. However, if you define the domain to be an open set, open 0, 1, let us say 1 by x, then this function is continuous but not uniformly continuous. So that means this delta will depend on the point x naught as long as will approach nearby to the point 0. 0 is the problem because 0 is you are having an asymptote. 1 is not the problem. 0 is the problem. Okay. That means now it depends on the domain whether continuity and uniform continuity both are same or different. That is one of the thing. And observation: if the domain is compact, then by looking into the graph, immediately we cannot conclude because both are same. Both are same. But if the domain is open, then since there is the variation in the function at nearby to x equal to 0, that means we can expect that this function may be losing its continuity, uniform continuity, nearby to the points where it is having large variation. Okay. So this is the relation between continuity and uniform continuity. Now let me observe. Let me point out one thing. Continuity is a local property. Local property means what? Means there are functions which is continuous only at one point but nowhere else. To understand the definition of point which I am making, there are functions which is continuous at only one point but nowhere else. That means it will be continuous at only single point, but at all other points it will be discontinuous. How is it possible? So you can prove it by using the density of the real numbers, q and q complement, rational and irrationals. So if you take fx equal to x for rational and fx equal to minus s for irrational, this function will be continuous at the point x equal to 0 but nowhere else. Okay, so that means continuity is coming out to be local property. It's not a global because you can define it at a point but not nearby to the point. Whereas if you go to the definition of differentiability, differentiability definition all of us know. This is the definition. And differentiability we need for mean value theorem, Taylor series, everywhere differentiability functions are needed, and to define the maximum minimum also differentiability is helpful. And now question is whether differentiability is also a local property or not. Local means can there be a function which is differentiable only at one point but nowhere else? Is it possible or not? So so idea is again the same function. You take fx equal to x square for x rational and x minus x square for x irrational. Okay, this function is not continuous except the point x equal to 0. And you can check that this function is differentiable at the point x equal to 0, but nowhere else. Well, except the point x equal to 0, this function will nowhere be differentiable. Okay, so that means differentiability also coming out to be a local property. It happens to be only at a single point, but nowhere else. Okay, so now the whole idea of this whole explanation is to give you a formulation of non-local properties which will come in terms of integration or fractional derivative, not in terms of differentiability or continuity. Okay, so that means what we have observed, continuity and differentiability are local properties, and in addition to that, this inclusion which is available in Wikipedia, that I'll ask you to check it because Wikipedia can have mistakes also. Okay, this inclusion on the compact set is also available. What what is the positive point of having this inclusion? Positive point is, you see that Lipschitz continuous function. Can you give an example of Lipschitz continuous function? Yes, if x equal to mod x. Mod x is not differentiable at x equal to 0, but except x equal to 0, it is differentiable everywhere if x equal to mod x. Okay, so mod x is not differentiable. That means there is no point of talking about continuously differentiable for mod x. But absolutely continuous function is a little bit larger set, which is containing also functions which are not differentiable at a point. So now for the next lectures, we'll see that these absolutely continuous functions will be used throughout. That means we will be dealing with the functions which are not differentiable at finitely many points or on a set of measure 0, but still we can differentiate them. What does it mean? It means suppose you take f is equal to mod x. F is equal to mod x is not differentiable at x equal to 0, but except x equal to 0, we can differentiate it. Okay, so this is how it goes. That means f is equal to mod x. We'll see that f is equal to mod x is also absolutely continuous function. Okay, so that means f is equal to mod x, we can find out the derivative. Let us weak derivative. We can find out the weak derivative of fx equal to mod x, which is not differentiable at x equal to 0. Okay, so this is what is this absolutely continuity part is I need to define what is called fractional derivatives, because this contains functions which are not differentiable. Okay, and I need to extend the definition of differentiability for the fractional derivatives. Okay, now let me come to what is called next slide. What is absolutely continuity? Simple way of giving the definition of absolute continuity is as follows. F is said to be absolutely continuous if there exists an integrable function. L1, I guess you know. What is L1? L1 means modulus of G is integrable in the interval 0b. Okay. If the modulus of G in the interval 0b will be bounded, if there is an integrable function such that fx equal to f0 plus integral 0 to x g dt. Right, understand? Then where g equal to f dash almost everywhere and f has finite derivative. So let us look into this part, exactly this part. Okay, so you see that if you differentiate this quantity and if you use Leibniz rule, then what will you get? F dash equal to g. That means f dash is not a continuous function because g L1 function may not be continuous. It means f dash may not be a continuous function. That is okay. In addition to that, we are also getting functions whose derivatives are discontinuous because g is L1. G may not be a continuous function. L1 function may not be continuous. You can take a step function which is not continuous. Okay, then step function is also integrable. Okay, so that means derivative of a function may have a jump discontinuity. It looks like f dash equal to some function which is f is, I'm not expecting the f to be differentiable, but I am expecting f to be almost everywhere differentiable, like mod x. Mod x derivative is what? Mod x derivative is equal to 1 for x greater than 0, equal to minus 1 for x less than 0. Okay, mod x is differentiable except at the point x equal to 0. Okay, that is called, you can tell it weak derivative or you can tell it almost everywhere differentiable, whatever it is. But this absolutely continuous definitions has a different structure. It says that your derivative part, whatever will come after differentiation, that should be integrable. You will see that there are a lot of functions which are differentiable almost everywhere, but its derivative may not be integrable. That will come. That means it is not like if it is differentiable, then it will be absolutely continuous. It's not like that. Okay. Now let us come to this one. This function is a continuous function, that we know. But this function is not a differential function at the point x equal to 0. At the point x equal to 3, it's not differentiable. And you differentiate this function, x at the point x equal to 0, you will see that whatever function you will get, f dash, that function will not be integrable. That means that function will not be absolutely continuous. So we'll expect, since when we'll be extending this analysis, we'll see that this function's fractional derivative will not exist, because this function, absolute continuity is a sufficient condition, one of the sufficient condition for existence of the fractional derivative up to order 1. Okay. Cantor function is almost everywhere differentiable. Cantor function, but not absolutely continuous. And you also have a function which is differentiable but not absolutely continuous. This function I'll leave it for an exercise to check that this function is differentiable, but it's not absolutely continuous. You check it. That means differentiable होने से भी मुझे कुछ I'm not able to get any kind of help. Okay. So f is differentiable may not imply fractional derivative of f exists. Why? Because for fractional derivative, one of the sufficient condition, not necessary, but one of the sufficient condition is f has to be absolutely continuous. Now let us come to the link. I said that the present work will try to give a link of fractional, integral, and differential equations. Okay. So this time we are trying to link between integral and derivative. Okay. Then after that we'll try to link between integral and fractional derivatives. Okay. So this link, let us look into. What does this link say? This link says if f is a continuous function, then it can do its integration. And if you differentiate this guy, that means if you differentiate the integral, then you will get back the f. That is kind of obvious, right? ddx of integral 0 to x equal to f. That is kind of obvious because you can use Leibniz rule. You just use Leibniz rule, you'll get it. Okay? However, jdf is not equal to f. Integral of differentiation is not equal to f. Differentiation of integration is equal to f. But integration of differentiation, that is not equal to f. That means integration and differentiation are not commutative apart. They are different. Okay. Now, like that, if you integrate 2 times, then you will get something like this. Okay. Let us skip the proof. Now, next question is, we got for every positive integer, we got, or for every natural number, we got a formula. The formula is giving like this. Okay. Question is whether this formula is valid or not if this n is taken to be a fraction, positive fraction, or negative fraction, or any real number. Okay. So one of the ideas, if you take gamma function is not defined for negative integers. Therefore, if you blindly substitute n by some real number, then this gamma function itself will not be valid. That means you cannot blindly substitute n by a real number. That is one of the part. Second part is, suppose I blindly substitute n by a positive real numbers. Then this gamma function is valid. This is also valid. Whether this integral is true for any kind of function or not. Any kind of function. Okay. Of course, the answer is not correct because not true, because you need to pose some conditions of the function f so that this integral is valid. Otherwise, why? Because this function for n less than 1 will go to the denominator, not in the numerator, but in the denominator. And that's why this f by x minus t to the power 1 minus n, this quantity will be having a blow-up situation. That means it may be unbounded. So you have to check this integral is defined or not. Okay. So blindly we cannot substitute. So for the definition of fractional derivative, like Caputo fractional derivative, what we do is we replace n by alpha, and then whatever we got, that will give as a definition. That is this one. This is the definition. Just replace n by alpha, a positive integer, by a positive fraction, not the negative fraction. Okay. Now we are having sufficient condition. If f is in L1, then this integral will exist. Therefore, I can start with the L1 function. L1 functions are dangerous. L1 functions are dangerous because L1 functions means what? L1 means Lebesgue integral functions. It is allowing you to have discontinuous functions which are having discontinuity at infinitely many points. Finitely many points are allowed, but infinitely many points are also allowed. Okay. Okay. Now let me come to this one, the definition of Riemann-Liouville. So Riemann-Liouville's definition, let us see. Riemann-Liouville's definition is a little bit linked with dn and jn minus alpha, where n is a positive integer. Okay, so that means if you write down the formally this definition, it will come out to be like this. Now, what is the problem in this definition? The problem is this part. If it is differentiable n times, then only you will be able to differentiate it. But this kernel is unbounded because it will go to the denominator. Therefore, there is no guarantee that this part will be differentiable at least n times, so that I can differentiate it n times. Now, question is, if it is not differentiable, then how do you differentiate it? Because you are giving a definition like this. the answer is okay. If it is not differentiable, then also it is okay. But you be sure you give a sufficient condition on the function f. Let us say f is ACN. ACN means what? F n minus 1 is a absolutely continuous function. That means f is n minus 1 times differentiable, and fn minus 1 is a absolutely continuous function. If it is absolutely continuous, then this multiplied with fn minus 1 will be integrable almost everywhere. Integrable, and after that, whatever outcome you will get, that outcome will be also differentiable almost everywhere. Okay, so you understood the idea. Idea is whatever is there inside this integral, that I want, that is definitely not n times differentiable, but if it is n minus 1 time differentiable total, and if it is differentiable almost everywhere except at finite limiting points, infinite limiting points, set of points of measure 0, whatever it is, then I can still find out dn dxn, and I can find out the Riemann-Leibniz operator. Yeah? What is the sufficient condition? Sufficient condition is this. If is this, then it will be this integral will exist. Now, with that definition, with some manipulation here, we also gave the definition of what is called Liouville-Caputo fractional derivative, which is given by this. What is the difference between these two? Difference is here the differentiation is coming inside the integral. There it was outside, now it is inside. What is the problem in inside and outside? See, if it is outside, then you are expecting something to be differentiable. But if it is inside, suppose this guy is rough, and this is coming to the denominator, not in the numerator. Therefore, total guy is rough. But after integration, since integration is a smooth operator, so you will expect that total outcome will be little smoother than what is given. Little smoother, little better than what is known. Not rough, but little. Since integrand is rough, so after integration, you will be expecting a little smoother than what is already there. But here, this total guy is rough, integration is smooth, but then after differentiation is rough, that means you will expect that outcome will be again rough, not the smooth one. Rough, because you are finishing by a rough operator, not a smooth operator. Okay, so this is what is the difference. And here is also a sufficient condition. If f is absolutely continuous function, then we can expect that this will be Caputo fractional derivative will exist. Okay. Now let me again try to link this one fractional derivatives with integral equations. Okay, integral equations. Okay. So how do you link it? Because integral equations are there in the calculus of addition. It is also there in the MSc syllabus. But fractional differentiations are mainly for research. That is not for MSc syllabus mainly. So how do you link it? Link is as follows. You have a function fn. Fn in general is unknown. You can replace fn by some functions, let's say u. And you also have a kernel function. And since alpha is less than n, therefore you will expect that this kernel function will go to the denominator. You will expect that n minus n is cancelled out and minus 1 is there. Therefore, this whole kernel function will go to the denominator. That means it will be a singular kernel or weakly singular kernel. Okay. So, since it is a weakly singular kernel, therefore it is an extension of what is called integral equation to weakly singular kernel form. Fractional derivatives are much more extension of to the weakly singular kernel side than from the regular kernel side, from the integral equation. It is an extension of integral equation to the much more bad functions. Sorry. Okay. Now we are also having some properties, like if alpha goes to n. So, can you see my slide when I'm not able to get it? Anyone? Who are there? 54. Can you see my slide? Someone, please respond.
Yes.
Huh?
Yes, it is.
Yeah, thank you. Sometimes what happens is if no one is there, if there is no response, it seems like I am teaching to myself. Okay, but it's not like teaching. It's like more on the interaction side. If you are having questions, then if I don't know the answer, then it will be good for me because I can try to find it out. What is the answer of this question? Okay. So now here you see that if alpha goes to n, then fractional derivative, Kaputha fractional derivatives are matching with the classical derivatives. But if alpha goes to n minus 1, it is not matching. That means because gamma 0 is undefined. So this is one of the good part what we saw in fractional derivatives. Constants derivative is equal to 0. Differentiation and integration. This is differentiation operation. This is integration. They're not commutative. That you know. They're not commutative even for integers. Okay. For fractional also they are not commutative. Okay. And d alpha 1 of d alpha 2 of f is not equal to d alpha 1 plus d alpha 2. Okay. So d alpha 1 like d alpha 1 d alpha 2 of f is not equal to d of alpha 1 plus alpha 2 of f. This kind of bad things you will see in fractional derivatives. Okay. My aim is not to complete all the slides. That is definitely not my aim. My aim is to complete only the basic parts. Only the basic parts. Okay. Now let us come to what is called Picard's theorem. Picard's theorem, we know that Picard's theorem holds for first order Kaputha fractional derivatives. Picard's theorem requires y dash equal to fxy where f is continuous and Lipschitz, continuous with respect to the independent variable and Lipschitz with respect to the unknown function. Okay. So this same thing also holds for fractional problems. So Pinot's existence theorem, that is called first order differential equations. That is d half u is equal to lambda times root u. This is not a differential function. And this function is having two solutions, ux equal to x and u equal to 0. That means the solution may not be unique. If f is differentiable, does not imply Kaputha fractional derivative of f exists. Okay. F is differentiable does not imply Kaputha fractional derivative exists. And fx equal to this is differential but not absolutely continuous. Okay, that I have already explained because one-time differentiability does not imply it is half-time differential. Though the formula says, that is interesting. If you look into the formula, suppose 0 less than alpha less than 1. That means n equal to 1. Okay. So that means it is f dash. And suppose you want to find out d alpha, d half. So question is, if f is one-time differentiable, can I say f is half-time differentiable? But then we got an example where one-time differentiability does not imply f derivative will be absolutely continuous. Okay. That means this integral may not exist. That means if f is one-time differentiable, it may not imply f is half-time differentiable. Very interesting. This is the example. And this is Picard's theorem, IVP, not BVP, IVP. IVP, it says that if f is a continuous function, and if f is Lipschitz with respect to u, and continuous with respect to x, then this solution of this problem will exist and unique. In addition to that, if f is continuous, you will be in Cn, means n times continuously differentiable. But that is not true for fractional case. Why? Again, I'm going to give an example. You just take an example, gamma 3 by 2. Gamma 3 by 2 is a constant. It's a constant. Just simple. Constant is infinite time differentiable. Constant is also an analytic function. So constant. So that means the force function f here, it's the infinite time differentiable. But if you look into the solution of this problem, it comes out x to the power half, which is not even differential function. At the point x equal to 0. Root x is not differentiable at x equal to 0. Okay. That means we cannot expect the function to be at least one time differentiable, even if force function is infinite time differentiable. That means whatever is there, which you have done in MSc, that you cannot copy paste to here. When you are extending it for integral equations, where the derivative parts is coming inside the integrand as a integrand that you see. Similarly, consider d alpha u equal to fxu. Okay. Consider d alpha u equal to fxu. So ui0 equal to ui, I equal to 0 to n, and we see that suppose I do want u belongs to Cn minus 1. Suppose I want that since alpha is in this interval, I want the solution to be at least in same order. Why do I want it? Because if you wanted to find this solution numerically, or if you want to find out an approximate solution of this problem, you need more smoothness than what is given. Suppose you want to use, suppose alpha equal to 1, and you want to approximate this one with forward scheme, or backward scheme, or forward Euler method, or backward Euler method. or central defensive. Then you'll see that you need more smoothness. If it is alpha equal to 1, you need at least 2 times differentiability or 3 times differentiability, like that. So that's why we always want the solution to be at least good in Cn minus 1. Then what is the condition you have to pose? The condition which you have to pose on the function f, because it is it's an input function, is this one. This is the condition which you have to pose to make sure that u is an n-time differentiable. But that is a very severe condition because f is coming from the model. After modeling only you are getting this f. Okay, you cannot pose that model should satisfy this condition. That is not possible. That means the solution of fractional differential equations are rough, and if you want to do approximate this by using numerical computation, you will expect a lot of difficulties because solution is not behaving smoothly. You need more smoothness, but you are not having it. If you want to pose conditions on for the smoothness, then these conditions are not feasible. It is not coming from the model, coming from the modeling. It is your posing to get it. Okay, that's why this problems are not easier to handle in terms of numerics, especially when you assume u is less times differentiable. Most of the publications you will see that they will assume u is in Cn or Cn plus or Cn plus 2. But if you do not know what is u from the model, how do you assume that u is in Cn or Cn plus 1 or Cn plus 2? U is unknown. If you can find out u, then only you can check that u is n-time differentiable or not. But if you don't know what is u, then how do you be able to check that u is n-time differentiable or not? That is not possible. So the assumptions are all rough. That is not possible, feasible in practice. Okay, and this is the best one which I was discussing about the first 2 slides. This slide is to show that fractional derivatives are not local. This means you can have function which is differentiable only at one point. You can have function which is differentiable only, which is continuous only at one point, but you can have function which is differentiable at only whose fractional derivative will exist at only over one point, but not nearby. Both possible. That is not possible. Why? Because at the end of the day, you are converting the derivative to an integral form. That is the integral 0 to x1 this plus x1 to x2 this. Okay. If you take alpha equal to 1, suppose alpha is an integer, then this part will be equal to 0. So basically, you will be evaluating x1 to x2 to the power 0 times f. Okay, that is very easy. And 0 to x, and if you take alpha equal to 1, this is to the power 0, this is to the power 0. That means 1 minus 1 equal to 0. This to the power 0 means what? This is equal to 1. x1 minus x to the power 0 means what? This is equal to 1. For alpha equal to 1, this whole integrand will come out to be 0. That means this part will be equal to 0, this whole part. But this part will survive as so that means fractional derivatives, classical derivatives are not are local into picture, but fractional derivatives are non-local because you have to find out x2 ux2 minus x1. You need the information, you need the integration from 0 to x2. Everything you need. So it is non-local. Non-local means you need more memory. So that says the computation cost will be high compared to what is called in fractional derivatives. Classical derivatives. Okay, this memory location is one of the important part. Kernels are also unbounded. Okay, so now let me come to how much time I'm having. Anyone is there online? How much time am I having? 10 minutes. That's a huge amount. Okay. Oh, 10 minutes is huge amount of time. Okay. So since I am getting 10 minutes, so I'll not explain each and every line, but I'll more classify on what is the difficulty we can face dealing with fractional derivatives, and if you are writing a paper, and if you follow those difficulties, especially, then you can publish it to a good journal, and you can tell that I'm having a publication in this journal, so I can go from college to university like that. Okay. So this is the difficulties. Let me explain, because that is more important for good publications, not for any publications, but for good publications. Okay? For example, let us take a model problem which is like this. Okay, this is the most simple model. Second order differential equation is there. You have a kernel. That kernel you can take weakly singular. That means kernel can be unbounded. You also have k number of fractional derivatives. That means as much complicated as you can do inside the model. Right? Only model. Huh? No, it's not time for the physical modeling. It is only just the model. We are taking a bad problem. We are proposing a numerical approach. You want to see that numerical approach is working for a bad problem or not. If it works for a bad problem, then we'll expect it will obviously work for a good problem also, because it's working for the bad one. Okay. So this is what the operator is saying. This is the unbounded guy. Each and every one is having unbounded kernels as well as derivatives inside the integral. And this part is obvious because now suppose I want to approximate this problem numerically. How do you approximate it? You have a second order derivative, so you'll be using most probably central difference for this one, because you also want higher order convergence. Central difference means what? Central difference means wxx equal to limit h tends to 0, wx plus h minus 2wx plus wx minus h by 2h by h square. Yeah? Similarly, you can also approximate wx by forward scheme or backward scheme depending on the sign of the convection coefficient cube. And you are also having a Volterra integral operator. This Volterra integral operator you can approximate by using Simpson's rule or trapezoidal rule. I have a question. I am posing the question. You think, because if some of you are researcher, then PhD is a scholar, then you have to think. Suppose I am using trapezoidal rule to approximate this integral. Trapezoidal rule. This is equal to fx. Okay. Then how many times differentiability is required to find out the approximation of this quantity? That I am giving an exercise. Or so suppose you want to integrate 0 to t fx dx, then how many times differentiability I need on the function f to find out the approximation of this integral by using trapezoidal rule. Similarly, how many times differentiability you need to find out the approximation of this by using Simpson's rule. That you take an exercise and find out. Okay. But we have a rough estimate on how to approximate it. And for this one, we have a differentiation inside the integral sign that I have just shown. So that means the differentiation also you have to approximate, that you can approximate by using forward or backward. And you are also having integration, which is a Volterra type. That means again you have to use some sort of trapezoidal rule or Simpson's rule. So we know how to discretize this guy, how to find out an approximate solution for this whole problem, roughly. So that we will be doing it. Okay, but the main problem will come into picture if so whatever approximation you use it. But when you show the convergence analysis of trapezoidal rule or Simpson's rule or forward scheme or backward scheme, there you need more differentiability, more smoothness for the solution. Okay, and we'll see for this kind of problems, especially when the time derivatives are coming into picture as a fractional form, derivatives with respect to time will be unbounded. This means del w del t is of the form 1 by t, where t goes to 0, it will be unbounded. So that is why these problems are difficult to handle, because derivatives will come into picture when you will do the analysis, inner analysis, convergence analysis. If it is unbounded, then your method may not converge, and whatever formula you are using, that is rubbish, because that may not converge. Okay. So these derivatives that will come into picture. Okay. So now how to discretize the time partition and space partition? You need the points. If you want to use trapezoidal rule, then you need also the points where you will be using trapezoidal rules. Mesh points we call, partition points we call. So how to do that partition? One of the way to use the partition in time domain is like this. It's called graded mesh. It's not a uniform mesh. If beta equal to 1, it is uniformly distributed. Beta is not equal to 1, it is non-uniformly distributed. You have heard about partition, right? In Riemann integration, you know what is upper sum, lower sum, partition, like that. Okay? So that this partition will come into picture in time domain also, space domain also. Time domain it is hard. Why? Because in time fractional derivatives are there. That's why it is tough. But in space domain it is not tough, because in space domain derivatives are smooth, derivatives are bounded. So I can simply use space domain to be a uniform size, very uniform partition. Okay, the simplest one. But for the time domain, I can use some sort of grading parameter beta, graded mesh. It is a non-uniform mesh. So the analysis will come out to be a little complicated than what you can expect on the uniform mesh. Okay. Then we have a lot of bounds that we can find it out. I'm not going into the details. And we also have fractional derivatives. If you look at the definition of fractional derivative, what it does is it approximates the derivative by using, this derivative is approximated by using forward scheme. And no, this is a backward scheme. This derivative is approximated by using, it's forward scheme. And this integral is approximated by using trapezoidal rule, trapezium rule. Okay, so totally you will get this scheme, this approximation for this derivative. It's equal, approximately equal sign. Huh? It is not exactly equal because you will be having some errors. And if that goes to 0, then only you can expect this is a good approximation. This part is a good approximation of this one. If the error goes to 0, error is not mentioned here. Okay, error will come in terms of derivative of W. We'll show the errors can be unbounded. That will not go to, that may not go to 0. Okay. Now again we are having a discretization for fractional. We have a central difference, we have a forward ordinal, and we also have irregular kernel, singular kernel, that will be approximating by using trapezium rule. And you can see that we are having second order derivative involved in the error. So what is the problem if we are having second order derivative? The problem is if it is bounded, then everything is fine. It will go to 0. But if it is not bounded, then what will happen? Like in this case, if it is not bounded, then derivatives will blow up. And the proposition which you are making for approximation of the solution, that will create problem. That will create problem. Okay? That's what I am saying. Okay? Now, this is the what is going to happen. You see that space derivatives are all bounded, but time derivatives are all unbounded. Because if k1, if k2 equal to 1 and alpha 1 equal to half, then it will be t to the power minus half. And t to the power minus half will go to infinity as t goes to 0. So nearby to the time t equal to 0, it will be unbounded. So that means the method which you know, like Simpson's, trapezoidal, immediately you cannot copy paste it. Okay. So then we developed a method. So I'm just explaining the tough parts. We developed a method to show that this will converge. Huh? So that convergence method is coming out here. It depends on the grading parameter beta. Now let me go to the example. Example is weakly singular kernel. Here you see this is unbounded. This is Voltaire integral operator. And here also integral operators are there with derivatives involved inside. Okay. So you see that there is a sharpness here nearby to the point t equal to 0. T's time domain is this one. At t equal to 0, there is very sharp. That means solution derivatives are unbounded here. Huh. Similarly here also. If alpha goes to 0, if alpha goes nearby to 0, then t goes to 0, it is unbounded. And our present convergence rate, this is the error. This if you increase the number of partitions in space and time, then you will expect the error to be decreasing. That's what is happening. If you 10 to the minus 4, 10 to the minus 5, 10 to the minus 6, 10 to the minus 6, it is decreasing as the number of partition points are increasing. And this is the order. Order means it is more than 1, almost to 2. So it is a order of convergence. Okay. Yeah, I am in the last slide. Okay, so this this work, those who are interested to have a collaboration with me, this is a collaborative work. Okay, this is a collaborative work with the people of ISC Bangalore and NIT Rourkela, and this guy is from IIT Bhubaneswar. It's a collaborative work. So those who are interested to have a collaboration with me, they're always welcome. And my email ID is prathimamay@gmail.com or prathimamay@itpdday, small letter. And of course, this is the last slide I'm having, as I told, that you're free to share your knowledge and ask me questions also. You can also the chat box.
Yes, ma'am. Am I audible, ma'am? I am not a professor, ma'am, up to now. I am a Dr. Pradeep Kumar, assistant professor. Okay, okay, ma'am. Am I audible properly, ma'am? Okay, good afternoon to all. I am Dr. Pradeep Kumar from Department of Mathematics in the Prastha College for Women University of Delhi. First of all, I would like to give my deep gratitude to the organizer for providing me the opportunity to deliver this talk. Though it is my first lecture in any kind of FDP, therefore I will try this lecture will be a good lecture today. Today I am going to deliver this talk which entitled with controlling chaos in cancer cell through mathematical modeling. In the today's lecture, I am concentrating upon the basic of my knowledge about this topic. As today mathematical modeling has a great relevance because we can relate with the system which evolves with the time. Therefore we concentrate for making a model for some biological system. Formally this topic this type of concept deliberately theoretically or arguing with the natural language, but with the help of modeling we can quantify the theoretical view. The fundamental cause behind this topic is involvement of computer in our life. Now comes to our presentation. This can you see my presentation? Can you see my presentation?
Yes.
Okay, my presentation is summarized into the four part. First is introduction, which consists preliminaries and main objective of the work, and the second is main concept for today's lecture, the influence of the temperature on cancer cell, in which we have to make we made a model for the tumor cells and we made a model related to the environment and see how environment impact on the tumor cell when we synchronize the environment model of the environment with the model of tumor with some synchronization scheme, and in the end we have some conclusion about this problem and we have application then references. Now there are some literature related to this problem like E.N. Lawrence, which is the first who made the 3D model which exhibit the chaos, and after that L.M. Pecora and T.L. Carroll talking about the synchronization of chaotic system with some scheme. Then I use the scheme introduced by Bai and Lagrange as which introduce the synchronization of two Lorentz system using the active control. Then I working on the problem which is introduced by Peliz and Randucase, and followed the problem of Peliz and Randucase by Etik and Bank. He introduced the chaos in three-dimensional cancer model, and recently S. Nikolov and all Vector introduced there exists a chaotic actor in the tumor cell. Now, there are some preliminaries for this topic. First is the definition of continuous system. A dynamical system or oscillator is defined as a system in which the system states change over time. If the system is continuous over time, an ordinary differential equation an ordinary differential equation and a set of beginning condition provide a mathematical interpretation of its evolution, like dp by dt is gpt, where g is a vector field there and p belongs to the rn, and g is the function which defines from rn to rn called the vector field, and p naught belongs to rn, which is the initial condition for this problem, this system. Now next is the stability in the Lyapunov sense. Actually, in the end, we have to show that after synchronization, the system is stable. Stability in Lyapunov sense, a solution phi t of the system is stable in the Lyapunov sense if for epsilon greater than 0, there exists del epsilon greater than 0, such that for any other given solution xi t of the system, then the absolute difference between phi t and xi t at the t naught is less than del. We have phi t and xi t less than epsilon for any t greater than equal to 0. Then next, because in this problem we have made a two new dynamical system, and shows that there exists the attractor in that dynamical system. Therefore, we need a definition of stage attractor in this case. So it is characterized by first one, in the phase space the attractor is of null volume, and the dimension d of the attractor is non-integer, like d lies between 2 to n, where n is the dimensions of phase space, and there is a sensitive dependence on the initial condition, that is two trajectories initially very close will diverge. Now, because in this problem we have made a system which exhibit the chaotic character, therefore the definition of chaos is also needed. So chaos is a periodic long-term behavior in a deterministic system that exhibit sensitive dependence on the initial condition. Here the periodic long-term behavior means there is a trajectories which do not settle down to a fixed point. Now, in this problem, again I told that we have made a two system which synchronize and define the synchronization between them. Therefore, we need to the definition of synchronization here, and we use the complete synchronization between that system. Thus, complete synchronization is defined as the state of the system of the interactive system, like P belongs to Qn to Qn, converge asymptotically to the same evolution, that is limit t tends to infinity pt minus qt is equal to 0. Here pt and qt defined as the error between system also. Now, because we exhibit that our system exhibit the chaotic character, and for this we have a measurement of sensitivity to initial condition through Lyapunov exponent, and Lyapunov exponent is defined like sigma I is equal to limit n tends to infinity, which is 1 by n log del pn over del p naught, norm of del pn over norm of del p naught. The Lyapunov spectrum is the collection of all the Lyapunov exponent. To ensure the occurrence of sensitivity to initial condition, a system spectrum must have at least one positive Lyapunov exponent. Now, in our problem, we have synchronized between two chaotic dynamical systems by using the active control synchronization scheme. Generally, active control synchronization scheme in which we consist subsystem which consists of two system. First system is called as a master system, and second system is called as a slave system. Then find out the error between that system by subtracting the second system, by subtracting the first system from the second system. And active control synchronization scheme is related to how to control the chaotic character in the chaotic dynamical system, for which we need to design the controller. Here dt, you can see in the equation number 6, dt is our controller there. Now see, for these we sum for identical chaotic system, we need to take B1 is equal to B2 and G is equal to H, then P and Q. For non-identical chaotic system, we need to take B1 is not equal to B2 and G is not equal to H, then P is not equal to Q. For synchronization of the system, we need to design the active controller, as I told. Then error system is given as I told, the subtraction of the first system from the second one. Here ET is defined as P minus Q. We defined the dynamics of the error as E dot T is equal to, this is the system of differential equation according as our dynamical system, and which is denoted by say E dot T is equal to Q dot minus P dot, and according to the system 5 and 6, which is P2Q HQ dt minus P1P and GP. Now our aim is to that is limit t tends to infinity, et is equal to 0, that is the error goes to 0 up to the time t tends to infinity or the time is very large. Then we get the stability in the error dynamics. Now comes over the main objective of this talk or of this work, to introduce the new chaotic dynamical system for the brain tumor. Actually I am working on the brain tumor cells and the environment. Also analyze the effect of the temperature on the tumor cell by synchronization of these two models using active control synchronization scheme. Now comes over the next slide. It is divided into following section: mathematical model of the tumor cell, mathematical model of the environment, synchronization between the tumor and the environment, and the conclusion. Now see how to design this model. So we have introduced a new chaotic dynamical system which characterizes the cell population into three classes, and each variable represents the cell population, namely PT the tumor cell, QT the healthy host cell near the tumor cells, and RT the active immune cell, with the following postulates: the growth of the tumor cell is non-linear, and P2 is the interaction of the tumor cell with immune cell reduces the activity of the host cell, and the presence of the host and the immune cell kills the tumor cell. With these postulates, the interaction between these three populations is shown by the figure 1. Figure 1 is the compartmental diagram between these three populations. Here first compartment, proliferation 1, which is related to the tumor cell, and non-proliferation 1, which is related to the immune cell, and proliferation 2, which is related to the healthy host cell. And this compartmental diagram is related to the interaction between these three populations. Now according to this compartment diagram, based on the interaction, the model consists the system of three ordinary differential equations. Categorize the change in the cell population given as follows: dp by dt is equal to minus APR minus Q plus P square. Here P square term represent the growth of the tumor cell is very high, because I want to see the result in the fourth stage of the cancer. Therefore, the growth of the tumor cell is very high in our case. And dq by dt is equal to minus PR plus C. Similarly, dr by dt is equal to PQ minus BR with the initial condition P naught, Q naught, and R naught. And for system 9, we take some particular parameter for our manipulation. Say A is equal to 5, B is equal to 2, and C is equal to 27. And by the with the help of programming in MATLAB, we find the Lyapunov exponent of this system of differential equation is 0.0 something. And here I told that one of the Lyapunov exponent is positive for exhibiting the chaotic character of the system. Therefore, we can say that this system is chaotic. Now, actually, I want to see the phase diagram of phase space diagram of this one, and very nice attractor is C, and I call this attractor as a wings attractor, new name, because this looks like a pigeon, wings of a pigeon. And we can see there exists a detector in this figure. Now, next model we introduced that a new dynamical model which characterize the interaction of microorganisms with the atmosphere. In a particular, we consider the interaction between the population of viruses and bacteria in an appropriate environment. And this model is based on the following assumption. First is particularly we include the population of Anthobacter. Actually, Anthobacter is a type of bacteria which present in the soil and which helps to maintain the temperature of the atmosphere of the earth. And initially the temperature is very high. This is the second assumption there. Based on this assumption, we consider the variable PT for the temperature, QT for the bacteria, and RT for the virus population. Now, this model is designed as a system of ordinary differential equation described as follows: dP by dt minus dP plus q. Similarly, dq by dt is equal to epsilon q minus pr, and dr by dt is equal to dpq minus fr. Here, initial condition for this system is p naught, q naught, and r naught. And for I also want to see that this system exhibits the Qs or not. So for this, we set the parameter for our manipulation is d is equal to 36, epsilon is equal to 13, and f is equal to 4. Then we can see that the Lyapunov exponent for this system is like 0.056150, and this is the positive Lyapunov exponent. Therefore, we can say that this system is also exhibit the Qs. And from the figure, we can say there exists a chaotic attractor in this system also. Now, our next work is to establish the synchronization between these two systems to see how temperature regulate the tumors, cancer cells. Now, for synchronization between these two model tumor cells and the environment, then we need to convert these two systems as a subsystem which consists as a master or the slave system according at the active controller synchronization scheme. If the system 10 is considered as a drive system and system 9 is considered as a response system, then drive and the response system is written like this, where U1 and U2 and U3 in the equation number 12 are the control function, and we need to determine these control function to synchronize these to control the chaotic character in these two systems and the synchronization to achieve also the synchronization between these two. Now, for this, we need to find the error between these two systems. For finding the error in between these two systems, subtracting the system 11 from system 12, the state error variable between the system 11 and 12 are described as like this, which is represented by the equation number 13. And then error dynamical system corresponding to the system 11 and 12 is represented by the equation number 14, which is E1 dot, E2 dot, and E3 dot, in which we need to determine the function u1t, u2t, and u3t. Sorry. Yes. Now, for finding the function u1t, u2t, u2t, and u33, we need to define that function as a equation number 15, like u1t is v1t, ap2 r2 minus p2 square bq1 minus dp1. Here we can manipulate this controller as we can synchronize easily these two systems, and in the end we find that our error system is linear system for converging the error system towards the zero as time t tends to infinity. Therefore, we can manipulate this u1t, u2t, u3t as the system 15 is reduced to the system 16 easily. Now, error system 16 to be controlled is a linear system with the control input V1, V2, V3. When the system 16 is stabilized by the control input, here V1, V2, V3 is to be determined, and these controller can be determined with the help of Lyapunov function. Stabilized by control inputs V1, V2, V3, then E1, E2, E3 will converge to a 0 as t tends to infinity, which implies that the system 9 and 10 system 9 and 10 are synchronized. To achieve this goal, we choose the control input V1, V2, V3 according this option of choosing V1, V2, V3 as A, E1, E2, E3. We have to determine this matrix A with the help of Lyapunov function, and with the help of Lyapunov function we have find this matrix A is defined like this: minus 1 1 0 0 minus 1 0 and 0 0 minus 1 into 10 raised to the power minus 10 raised to the power 5. Here we can see that all the eigenvalues of this matrix A is negative. Therefore, we can say that the limit t tends to infinity, t goes to 0 for this particular choices of the matrix A. Therefore, we can say that according to the active control synchronization scheme, we can say that the synchronization between these two systems have achieved. Now, according to the figure 4, we can say that the dynamics of the synchronization error state goes to 0. Therefore, we can say that the synchronization between these two systems have achieved, and we can say how temperature affect the tumor cell. So now comes over the conclusion of this work. This problem demonstrates that the growth of tumor cell may be controlled with the change in the temperature by synchronization it with the help of an active control design scheme, and we observe mathematically that temperature may regulate the proliferation of the tumor cell. The solution of this synchronization problem of brain tumor may aid to oncologists in determine how much resistance the patient and disease have, when the tumor cell can be increased or decreased in the number or size as well, and which climate condition are the best for the tumor therapy also. Now application of this problem, because these two models are the new models, therefore there are wide application of these models, and I am using this model for the further study because the justification of these two models are also remaining. Now these models help to researcher for gaining the better knowledge about how drug synchronization with the cell and control any uncontrolled or chaotic behavior in this interaction, which could lead to getting better treatment option in the future, as well as in increase the quality and the length of the patient life. Then these are the my references main, and thank you. Any questions?
Sir, if you can please share your PPT. Hello.
Share my PPT.
Yeah. Into
Okay, I am sharing my PPT with the organizer.
my email ID.
Okay. I am sharing my PPT and email ID to the organizer also.
Sir, I have sent my email ID into the chat box. Please send the
Okay.
sir. Actually, your presentation was very nicely explained with basics. Sir. That's why I'm interested.
Okay. Actually, you can write my. There is some technical glitch in my mobile. Okay. I can see the message now. But okay. You are Arun Ashram 9. Am I
Yeah.
audible?
Yes, sir. That's my email address.
Okay. I will send my PPT on this mail.
Okay, sir. Thank you so much.
Okay. Is the end, ma'am? Yes, ma'am.
Just give me, okay. Can we start now? Okay, okay. So, thank you very much, Dr. Krishna Das, for inviting me to share my experience with the galaxy of young mathematicians and scientists. So, welcome you all in this talk. Basically, the talk, is based my personal experiences and research during the last 20 years. So nothing is, from here and there. Things totally depend on my, discussions and research. So we will enjoy, and basically I prepare this something for the young guys, because most of the people, are talking about the subject, but the young guys needs the way, the how to deal the publication problems and how to publish good research papers, because nowadays it's demand for the publication in each and every field, the natural science, the social science, and the others as well. So I think this is good platform to talk about the young people, about the way to handling the, the publication and the problem faced by you guys. So in these 30 minutes, we will talk about on this issue. So let me share my slides first. Give me a few minutes and come back after sharing my. Okay. So, okay. Yes, this slide is visible. It is visible. I hope I'm audible to all of you. My voice is clear. So, dear colleagues, this is not, the teaching as usual. So it is totally, the different from the usual teaching, and we are discussing, not only talking. So feel free, when you have a question in your mind, please just come in the forward and ask me. So we will make clear at the moment, not later on. So I hope this is for 30-minute talk is not enough, but try to give you the brief account on some tools to write good research papers in pure and applied sciences. So this is Professor Shakir from Aligarh Muslim University, Aligarh, working in the field of algebra and its applications like coding theory, cryptography, and graph theory. So I will share my experience, the public publication handled by my team and me in this area. So then this is the brief, about my university, and just outlook, not give you more detail, and come on the topic we are going to talk right now. So, dear colleagues, these are, we always try to publish in good publishers, and so I choose not large, but some key publishers or whom I and my team are published, are in process to publishing, and the problem faced, and then how to handle these problems with these publishers. So these are the few, like Cambridge University, De Gruyter, World Scientific, Wiley, Taylor and Francis, Spenger, IEEE, Elsevier, and Academic Press. So almost most of the publisher, they have some of the common rules and common point for the publications, but not same in every way, but some point is common, not every point is common. Okay, because different have the different, the style of the praise, and sometimes they ask for the text file, sometimes they ask for the word file, depending on the publishers, and so on and so forth. So let me come on the outline of today discussion. So briefly, we talk about the title of the manuscript. What is title? How to choose the title, and how the title look like. Some author's information means about your affiliation, how to put, and where and when, means at what place you put your informations. Then abstract, what is abstract and how to choose your abstract. Some keywords and why the keywords is important, and subject classification, what is subject classification and why it is needed. The main body of the paper, and then acknowledgements and the references and supplement material. So we follow just one by one and give you some tips how to choose these points to make your paper in excellent form. Yeah. So let me come on first, title. So what is title? So title, it summarizes the main idea or the idea of your study in few lines. So the good title contains, the first possible words, adequately describe the content and purpose of research paper. Means the title of research paper should be the short and effective. So how do we do it? The title of your paper is, this is what the first, the outsource, and which gives the first reflection in the eyes of, the managing editor and researchers, means referee as well. So title gives the whole, means the few lines, few words, one line will give the idea what the body of your paper tells us. So it choose very, the smartly and if way which gives the overview about your the manuscript. Okay, and then these are the some way to pick up the title. Like title should be the concise and the small, not more than 2 lines. Preferably is 1 line is enough. Even okay, so always choose not more than 1 line for the better title, and it should be the informative and complete. Means give the whole idea about your research papers. And of course, as I told you, the title of your research paper attract, the first impression in the mind of managing editor, and of course, the readers as well. So very, very important component of the manuscript. A title does not contain infrequently used abbreviation. It means do not use. Sorry. Okay. So be careful when you decide the title of your scientific writing. It really is attractive to the readers always and smart. That gives the background of your manuscript, scientific writing, you can other words. Okay. So what should avoid in the title? This is very, because some people do not think the title is the first, that give the impression in the eyes of the managing editor, referee, and most importantly is the readers. So there are just few ways to avoid the titles, such as like on conjecture on Ahmad and Khan, like Prasad and Kumar. Really, that does not convey the information what to do, the insights. So always avoid such type of title of your manuscript. Okay. And also avoid the technical terms. Do not do the short form in the title. It's important. And then about the information. Basically, this is very important point, and this means where you put the informations and in what way you will put information about the author or authors, or if you had more than authors, then how, because many of the journals, they already mention on their home page where you have to write the author's name on the front page, the bottom of the front page, or on the back side of the last page of your manuscript. So these informations basically related with the the publishers. Each publishers have their own way of writing. So in that context, my suggestion is, whenever you have mind planning to submission a manuscript, please go through the guidelines, like the author's guidelines for the authors at the homepage of journals. So most of the journal, they already mention where you have to put the author's information and the affiliations. Like in particular, there are so many papers, like if you're talking about the algebra of science, they are asking, put the author's information on the first page. Your name, your affiliation, and email. Okay. And like, Sponger, sometimes they ask the author's name on the front page, but address just on the bottom. Okay. And also the important point, some of them they ask, please write clearly the name, email address of the corresponding authors. Because the corresponding author is author who will make communication with the journals. So these points will help you to give you or to help to editor or reviewer, mainly the editor, who or whom he will correspond whenever he or she has a problem. So for the author's information, the suggestion is, please visit the homepage of the respective journals and check where you have to put these informations and go accordingly. Otherwise, what happens if you submit randomly your manuscript, okay, then after a few weeks they return you back and ask you, please put the information according the according the rules of journal, and it will take sometimes the 3 weeks or 4 weeks or month. So this means you are wasting your time. So do not do that, and it's the best way to check the home page of the journal. And then, the key component and most important component of the abstract of your manuscript. So this is what, in other words, abstract should be the advertisement of your manuscript. Like if you want to sell something in the market or to attract the people, you will put, your advertisement on many places, sometimes on Middle Road, sometimes on the bus, means depend on the type of the product. And So you make the wide advertisement of your product. Your abstract is like the advertisement of your manuscript. So the choice of abstract is most important whenever you finish your article and then you write your abstract. So it is the key component of the research paper. So keep it simple, informative, and attractive. It must follows by the title, because your abstract and title, they must have some, the common way. They must be related to each other. Moreover, the quality of an abstract will be strongly influence the editor's decision. That I told you, because the first thing editor or referee see your title and abstract, and then go inside. Otherwise, he sometimes just return the article while reading your title and abstract. Okay, so the title means the abstract of your manuscript is, is attractive, and that give the best impression to the editor and the referee. Yeah, in other words, you can say an attractive abstract put the editor and the referee in good mood. If they read your abstract, it means title and abstract, they make decision. Okay, yeah, we will go in the positive direction because the author put the good things in the smart way. So it is one of the most important component of the manuscript. Be careful whenever you writing the abstract. It should be attractive and informative. In few lines, like 4 to 5 or 6 lines, is enough for the abstract of it. And in the abstract, in fact, similar to the title, you also avoid something like many of the journals do not need the citation in the abstract. Okay, so be careful whenever, as I told you, in the context of this before the submission, you should read the guidelines that are given on the homepage of the respective journal. Okay, it's very, very important. Do not use the technical jargons. Be careful. Do not write, because the people will read, and if you using the terms which are not, related to your manuscript, may be the cause of the rejection. So please do avoid such things. Now, keywords and phrases. The keywords are important and very helpful to the editor, because editor will keep in mind these keywords and try to search referee, because some journalists, they never ask you to provide the name of referee or anything. They just follow your keywords, and on the basis of your keywords, he will try to select a referee. Okay, similar, the American Mass Society decide about your area, your expertise, based on your keywords, because if you give these keywords give the information about your research activities on the subject. So these are the important, and most of the article, they must contains keywords. Even not the editors ask you provide the keywords, because they are the important in indexing and help to editors and referees. So these keywords and phrases are important for the in that context for the editor and referee for the refereeing process, and for American Mass Society decide about your the further review. Subject classification, as already this is American Math Society. Like presently, right now, we are using American Math Society Subject Classification 2022. In some journals, they write just CMS subject classification, and some journals, they ask primary or secondary. Okay, because subject classification is very helpful for American Math Society to review your manuscript. Okay, that's why for each and every subject, you find the subject classification on the side of American Math Society. You go and decide. Okay, and the most close area is called primary and follows by the secondary and tertiary classification. These all the informations are available on American Math Society AMS review for each subject. So now we come on the main text. Results, conclusion. Hello. Krishna Das. Hello. Dr. Das. Dr. Das, I'm audible. Hello.
You are audible, sir, please.
Any question or comment till now? Any question or comment? No. Okay. So let me proceed. Okay. So come on, you know the main text. So the main text of the research manuscript divide in three parts, mainly introduction, results, and conclusion. An introduction is the most important component of the manuscript. It convinces the readers that your work is important. Research papers should be neat and attractive and beautiful. It gives the very positive impression to the referee who make decisions. So your manuscript, as I told you, they involve three parts, introductory part. The first part of, if you divide your introduction in three parts, as again, the first part you make like, you know, the key notations and definitions. Second part, you give the background of your work, whom work you are following, and then write down the third para for your own work, what you want to do. Okay, means motivated by the previous section. Our front is to prove the following results. Write down the short form of your results. So your introduction also give the background of the material presented inside. Okay, and then, you know, the main contest, just continue to start the section by the key definition, write the general background of the topic, write 2 and 4 paragraph, discuss work of the previous authors, means your motivation. What is your motivation? So write 2 and 4 paragraph on the motivation. Okay, and finally point out the issue that are being addressed in the present work. That part is your part. This part means not your part. This is work done by the any other authors. So this is very important, how the English terminology will use, that in future tenses we will use, and how will we write down the other areas. Okay, so means this part is very important in the point, because this gives you whole about you. How are you doing research? Do you following some, you know, the criteria for English or the other things? This is very, very important part, and you have to decide which sentences and where you have to these sentences, where you use the present tense, where you use the past tense, and so on and so forth. Okay, so that is the important means the way to decide. Also, there are some you know, the tips what you have to avoid, like less. Don't say like is it better than the others, or my work is better than to others, or do not use such type of comparability. Maybe you can say the same thing in other words, but do not remark directly which gave not good impression about you. Exit presentation without any discussion and citing every argument with published work. This is very important. Whatever you used from the other authors, do cite it, please cite it, and give the whole weightage to the those who have already published their own work in the field. And then we come on the main results part. How to write down results. What should be, how to arrange your results. So in that context, finding the form like lemmas, proposition, and theorem. Sometimes you will start some definition, give some examples, motivation, or like that you can say this like means something is not true for this. Okay, you can give the counter example and then write down your objective, because we are going to the bay which not satisfy this. However, if we do like that, it is whole. So give these all things the basic results, okay, that you use your main results like lemmas and propositions, and finally you give the theorems. Highlight the difference between your work, your results, and the previous publications. Like if you generalize your work from the previous studies, so it is better you should write the corollary of the previous authors that give the basis for your work. In the term of, you can say, you write some consequences of your findings, and these consequences definitely give the basis of your own work. So divide in that way. And then, when you finish your results, consequences, and then you can move towards the conclusion part. And the conclusion part is also gives the short summary of your findings. So a conclusion should be clear, and that help the viewers to judge your findings in very short of times. And also you give the new direction for the authors or those who are working in your area by giving the direction in conclusion. So the key findings are followed by brief discussion for the future perspective. This is what the conclusions means. And again, conclusion and abstract, they are very similar. So do not put the abstract in your conclusion, because both are different things. If you write all these, means you write your abstract here, it's not good thing. So I'll always avoid. It must be different from the abstract. Okay. So do not summarize the paper, means what to not do in the conclusion. Do not summarize the paper. Do not make the trivial statement. Okay. And do not use the uncertain words, probably, might be, or maybe. Because conclusion is the part where you can explain done or not any other things. So be careful always. Do not do such things in conclusion. Okay. And then we come on, the acknowledgement parts. This is the last, of course, last part, and what to do and what to put in the acknowledgement. So the manpower who helped in any way to complete the manuscript, it may be, your office staff or some colleague or some other people, so must thank in that part. project fundings and other agencies, like if you have some fund, then definitely you will give the fund informations in the acknowledgements. Or moreover, if you are visiting some universities, some colleges, okay, and they give you fund, they support, they give you, so you can say things also in that part. So acknowledgement, they involve all these things, and that is very, very important. Do not avoid, because this is the author's responsibility to say things for those who helped you in any way to complete your manuscript, and the funding agency who support your research. Okay, and also referee, most important, because he is without any money, anything, he or she will read your manuscripts, maybe take 1 week, 2 weeks, sometimes more time, just without any, again, this is just honorary job. Okay, not some of journalists, of course, they are paying some, the points system. Maybe like if you review one paper, they give us 100 points, equivalent to $100. But even then, they not give you the money. So the referee job is just a free race, moneyless. So at least we should say thanks to the referee in acknowledgements. And references, yes, very important, because you are using the work of the others. So write complete list of all cited references according to the style of journals. This is also because some journals, each journal have the different criteria to write their references. So in that context, my suggestion is go to the journal home page and read their guidelines how to use references, the bay. And the most common bay, so many journals following, that is the American Mass Society style, but not more every journal. There are still journal has a different area. So be careful, okay? And check guidelines for the authors of the bay page of the journal, since it varies journal to journal, okay? Write correct spelling of the authors, year of the publication, volume. Sometimes what happened, because as a reviewer, as a referee, I noticed many papers, they write, the authors give, the inside, they prove the good result, but they are not making, they are careless when they are dealing the English writing. They write wrong spelling of the authors, even, and wrong year of publications, volumes, so on and so forth. This part is very important, because the referee are, suppose if you're writing my name and I'm referee of that paper, if you're not writing the correct spelling, sometimes it is get very bad impression in the light of your work, and sometimes it may be the cause of the rejection. Very, very important. Do not put the things, even do not take any short communication, short paragraph carelessly. Each and every line should be read and edited very carefully. Punctuations uses is a very, very important. Yes, of course, this base. So careful, choose all these things. Otherwise, sometimes we face paper bill rejected by the referee. Supplement material. In this section, artists should include the following. Sometimes, like I am working in coding theory, so my journals or some referee asking which program or which tools you are used. Could you provide your program? Because you want to check really you are use this program or not. So we can put this program in the last part supplement material. And what happened, even sometimes they ask a proof, some proof for the referee, because maybe they ask how do you do analyze. Analysis or additional data if necessary. So all this part known as supplement material. And what happened in fact, when the referee agree, then he or she will advise, now you can delete your supplement material. Otherwise, journal editor or the publisher will advise you what to do next. But it is important, if you're using some new technique, if you can put over here program or some short proofs. That will be help to the referee as well as the editor inside. Hello? Hello? Dr. Krishna Das. Hello? Okay. So, my dear colleagues, here is some material, because as I told you, there are a lot of things you find how to write a research paper. So here I just give you some references. You can use these references like scientific writing, research article, Strategy and the Steps by John Wiley since 2021 by Cargill and Codd. Similarly, the art of scientific writing is also important. They provide the way, okay, how to write these good or excellent scientific writing, or how to get good research published in journals. This is, you can find many such means tools and technique in these two references. Some yes, how much time I have, Dr. Krishna Das? Hello. Yes. Okay. So I'm near to conclude, because I try to demonstrate something, but if you don't have time, then I can conclude right now. Here we using very means of some examples. Okay. What are the problem, how we write down. Okay, that's I like we are a mathematician, so we write a result. Okay, this, but the aim of this paper is to prove the Sarbajan-Hassan result with pair of derivations around prime ideas with relation. So exactly, let the exactly be proved that if our ring is with relation admit to derivations given means to maps which satisfy this condition, and if characteristic of this is not true, then this is commutative integral domain. So how how to write the half of the result? So there is a problem. Okay, so like that, if there is a non-zero derivation d of r, this happens. So this is not give the complete information. So in other way, how to say, so exactly part followed by this, and where you use the if, and how the if followed by then, like that. So here we give some examples. If characteristic of this is not true, then the dr over the content in PR, so on and so forth. So this is just make some hint for those who like. And next part is how to make, as I said in the initial stage, the connection between abstract and the title. So look over here, I demonstrate here the characterization of left centralizer maps in rings. Okay, but when we say in the title, look over here, I'm going just to give the last part. The main purpose of this paper is to characterize Jordan left centralizer. So in here we say the Jordan left centralizer, and here we say the left centralizer. So in order to make very the symmetry is better, but is to use Jordan left centralizer. So that make connection with your abstract and your title. This is the meaning. This is one second demonstration for in that context. Be careful. Always titles is matched by abstract. Okay. And now I just going to close. So you can also find some extra tools if you have time. Like if you go the algebra science, then put on algebra science. They give the way known as, this is called Algebra Publisher Campus. When you go on the Algebra Publisher Campus, you can find all technique or the way how to submit your paper, how to do that, you find on this platform Algebra. Similarly, Taylor's and Francis Author Service. You go over there, click and found. Wiley Author Service, yes, they also provide the guidelines. World Scientific Author Service. So the most of the international publisher, they already have a platform and where they provide and discuss some tools and tips for the authors. And this is the end. And thank you very much to all of you. Yes, that's the dust. Just I finished this. Can I stop the sharing? Do you have any question or comment from the audience? You are welcome, please. No. Welcome, welcome.
Is it visible? Hello? Okay. Mathematical modeling in COVID-19. Sir, this slide also visible, sir? Does it? Okay, okay. First of all, the welcome to all the participants. Mathematical modeling in COVID-19. This is old topic, you know that. Old topic means 2 to 3 years before 2020 we started. A lot of the mathematical modelers was very happy due to COVID-19 time, because all the papers, most of the papers published due to COVID-19 models. At that time is a very pandemic. This is one of the very pandemic disease. We got a lot of difficulties for this, you know that. Right now, a lot of variants are there. Delta variant, alpha, beta, lot of variants are there. The same equation, if you change some slightly modification, you'll get the new equation. Otherwise, you can go the previous one, TB, HIV. HIV also, you know that. Right now also doing modeling from HIV, TB, HBV, Nipah virus, lot of diseases. So there is no end for the mathematical modeling in biology. There is no end. So this is also a good topic in research also. But you can select for some another variant, delta variant, alpha variant, or other any new modification required for the already published equations. Okay, this history already you know that. So directly we are going to the model. The introduction to COVID-19, this all already you know very well. These all are introduction. It's a overview. These all you know that is a common things only. The prevention, most common symptoms: fever, dry cough, tiredness, everything you know that. Less common symptoms you know that. Serious symptoms also you know that. Okay. The measures of transmissions. First, initially at the time of COVID-19 period, um, American people initially started one transmission based paper published from USA. The same paper has given some guidelines. And from the guidelines, easily understood the basic concept. Or not reproduction number basic concept easily understood. Then after that, we are going to some infectious diseases model. We'll get all these things. First, the measures. These all measures are 2020 end, maybe 2020 end. These measures identified from USA people. The measures of transmission, three things are said initially. Attack rates, basic attack rate, secondary attack rate, susceptible exposed attack rate. So AR, SAR, SEAR, these three are set first attack rate. Then reproduction number. Generally we discussed for all mathematical modeling in biological papers. Mostly we discussed, except reproduction number, we don't do any other models. Stability also compulsory need for reproduction number. From the reproduction number, generally we said greater than 1 and less than 1. The cure rate is less or high. That is common to all the papers. First one is attack rate. Said some three basic formulas initially said by some scientists. First one is attack rate. First one is raw attack rate. Attack rate means here AR equal to number of cases. Number of cases means total pi. Number of cases total 3. These 3, the red lines. These red lines, these all are cases. So 3 cases. Total population size is 5. So 3 by 5 equal to 60%. This is the attack rate. Then another one is SAR, secondary attack rate. Secondary attack rate, one formula. Here I minus 1 by n minus 1. Here the infection totally this diagonal you will see totally 3 minus 1. 3 minus 1 equal to infected rate. So 3 minus 1 equal to 2. Here this population 1, 2, 3, 4. This one n minus 1 is a population. Total out of 5, 1, 2, 3, 4, 5. So n minus 1 population. So 4. So here 2 by 4 equal to 50%. This is secondary attack rate. Okay. Then another one is the susceptible exposed to attack rate. This is also very, very important things. Here in our SEIR model, here lot of exposed model. SIR model converted to SEIR model. SEIR model converted to SE exposed and E quarantine also. Here many papers published. One compartment in the susceptible at exposed rate. SE. Susceptible also, quarantine levels also posted. So S and SQ. EQ. Q means quarantine. So EQ, both identify. So yeah, in a single equation, in a single model, mathematical people formed a lot of formulas, lot of models in nonlinear differential equations. Okay, the susceptible here, the same susceptible, and another one is exposed. Attack rate. These two are very, very important. The another one is that is a recovery infection. Mostly it plays very big role for this four compartment SCIR. If you know this all those things, you can add susceptible becomes another two compartment SQ. So susceptible susceptible at quarantine 14 days already given. So SQ exposed is